My name is Sanu and I am student of chemistry honors second year. So today we will read the chapter Chemistry of the Lanthenoid Elements. Introduction. Lanthanides, also sometimes called lanthanones, are the elements which constitutes a distinct series of 14 elements from cerium Z equals to 58 to lutetium Lu Z equals to 71. They are so called because these elements succeed lanthanum LaZ equals to 57, the element of group 3, and lie between it and hafnium HF Z equals to 72. The elements of group 4, both belonging to third transition series or 5D transition series, that is why they are also known as inner transition element. These 14 elements belong to F block and are the member of 4F series because the last of differentiating electron in the atoms of these elements enter 4F subshell. The F subshell of anti-penultimate shell here n equals to 6. Thus F block elements have partially filled F subshell of n to second shell in the elementary or ionic state. The first and the last element of the 4F series have been mentioned above, like Ce and Lu. The rest 12 elements along with their symbols and atomic numbers are given below. Praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium. In analogy with various series of D block elements, these elements are called first inner transition series element. All the 14 elements of these series resemble closely in their electronic configuration and the chemical properties with one another, as well as with the lanthanum, which may be called a prototype of lanthanide element. All these elements said to be the member of group 3 SC group and have been allotted one single position in the periodic table. These elements were originally called rare earth elements because the elements then known occurred as oxides, earths, and were available scarcely. All the elements have similar physical and chemical properties, hence are considered together for the study. It is interesting to note that the elements with each atomic number are relatively more abundant and also have larger number of isotopes, but those with odd atomic numbers are less abundant and do not have more two isotopes. Promethium Z equals to 61 has been made artificially only and does not occur in the nature. Electronic structure of lanthanides. The electronic configuration of lanthanides have been derived from the electronic spectra of the atoms of these elements. These spectra have great complexity, thereby referring to some doubts about the configuration in the following tables. The expected and the alternative probable configuration of elements have been listed. The expected configuration have been derived by taking into account the electronic configuration of lanthanum and supposing that in all lanthanide elements succeeding lanthanum, additional electrons are filled as 4F subshell successively from cerium to lutetium. Thus the 4F electrons are embedded in the interior while 5D and 6S electrons are exposed to the surroundings. According to the later view, as is evident from the table, the solitary 5D electrons shift into the 4F subshell in all the cases except GD 64 and Lu 71 because it is favorable energetically to move the single 5D electrons into 4F orbital in most of the elements and give more appropriate electronic configuration which is widely accepted. In GD, such a shift would have destroyed symmetry of a half-filled F subshell and the resulting configuration would have been less stable than the portable configuration. 4F7 is more stable than 4F8 configuration in the lutetium. The F subshell is already completed fill and cannot accommodate by any additional electrons. From the above, it may be concluded that the general electronic configuration of lanthanides element could be written as xenon n-2F 1 to 14 n-1 d 0 1 ns2 where n is the principal quantum number. Example 6, the 3 subshell n-2 f n-1 d and ns together forms the valence shell of these elements. 4f 5d 6s equals to valence shell. Oxidation states. It has been shown that lanthanide elements are highly electropositive and form essential ionic compounds. It is observed for these elements that +3 formation of tripositive ions Ln3+ is the principle of common oxidation state exhibited by all of them. This is said to be most stable oxidation states of the lanthanides. Some of these elements also show +2 and +4 oxidation states, but except a few such ions, they have tendency to get converted +3 state. For example, SmCe from Sm2 plus and Ce4 plus ions, but are easily converted to plus 3 state. That is why Sm plus 2 is good reducing agent, while Ce plus 3 is good oxidizing, plus 4 is good oxidizing agent. Sm2 plus gives Sm3 plus electron provider a reductant. It means Ln2 plus and Ln4 plus ions are less frequent than Ln3 plus ions among the lanthanides. Plus 2 and plus 4 oxidation states are shown by elements, particularly when they lead to noble gas configuration, half-filled orbital, या completely filled f orbital. Inorganic chemistry have among the above plus 2 and plus 4 oxidation states which exist only in aqueous solution are exemplified by Sm2 plus Eu plus 2, Yb2 plus and Ce4 plus. There are some exceptions also. Sometimes plus 2 and plus 4 oxidation states are also shown by the elements which are close to F0, F7 or F14 states. Example, the valence shell configuration of the ions given below are F1, F2, F3 or 4F6 and 4F8. No satisfactory explanation for these exceptions has yet been given. The oxidation states have only been explained on the basis of thermodynamics and kinetic factors. The two arbitrary due to the only one stable oxidation plus 3 lanthanide elements resemble each other much more than do the transition or D block element. It has also been observed that the higher oxidation state of the lanthanides are stabilized by fluoride or oxide ions, which the lower oxidation states are favored by bromide or iodide ions. Among the lanthanides, in addition to plus 3 state or plus 2 state is shown Nd, Sm, Eu, Tm and Yb only, whereas plus 4 state is exhibited by Ce, Pr, Nd, Tb and Dy elements. Rest 5 elements shows only plus 3 state. Ionic radii and lanthanide contraction. Here ionic radii of tri-positive ions have also been considered because plus 3 is the most stable and common oxidation states of all the lanthanide in the general. The atomic radii of these elements also decrease from Cu to Lu, but the overall shift is only 165 to 156 or 9 pm. These values do not decrease regularly like ionic radii, rather than are some irregularities at Eu and Yb which have abnormally high atomic radii. The atomic radii for the metals are actually the metallic radii which are recorded for the metals atoms surrounded by 8 or 12 nearest stable in bulk. Various metals atom in metal crystal are bonded together by metallic bonding. In Eu and Yb, only 2 6s electron participate in metallic bonding. 4f subshell being stable. For other lanthanide, 3 electrons are generally available for this purpose. These result in larger atomic volumes of Eu and Yb because of weaker bonding among them. The larger values ultimately gives rise to larger size in the atoms, the element. Cause of lanthanide contraction. As we move along the lanthanide series, the Cu to Lu, the addition of electrons take place of the 4f orbital, one at each step. The mutual shielding effects of f electrons is very little, being even the smaller that the d block due to the scatter or diffuse shape or these orbital. However, the nuclear charge goes on increasing by 1 unit at each step. Thus, the attraction between the nucleus and the outermost shell electrons also goes on increasing gradually at each step. The 4f electrons are not able to shield effectively the attraction of the nucleus for the electrons is the outermost subshell, or the atomic number of lanthanide element increases. The result in the increase inward pull of the outermost electrons by the nucleus, finally causing the reduction in the atomic ionic size of these elements. The sum of successive reduction gives the total lanthanide contraction. It may be concluded that lanthanide contraction among the 4f series element and their ion takes place due to the poor shielding effect of 4f electrons and gradual increase in the nuclear charge. Consequences of lanthanide contraction. Lanthanide contraction plays an important role in determining the chemistry of lanthanides and heavier transition series elements. Some of important consequences of lanthanide contraction are discussed below. Basic character of lanthanide hydroxides. LNOH whole thrice. Because of the size of tri-positive lanthanide ion decrease regularly with the increasing atomic number or nuclear charge, the process being called lanthanide contraction. Therefore, the covalent character between Ln3 positive ions and OH negative ions increase the LaOH thrice to LuOH thrice. Fazan's rules. As a result, the basic character of the hydroxide decrease with increasing atomic number. Consequently, LaOH thrice is the most basic while LuOH thrice the least basic. Second, resemblance between the atomic radii of the second and the third transition series. The lanthanide contraction is the most important factor allowing the separation of lanthanides from the one another. Also, it is significant effect of the relative properties of the element which precedes to succeed the lanthanides. Normally, the same group, the atomic radii increase as the value of principal quantum number increase due to increased distance between the nucleus and the outermost shell of the electrons, which counterbalance the increased nuclear charge. The fact is evident, which the values of atomic radii compared for the elements for the first and the second transition series on the same analog, the atomic radii for the element of the third transition series should be greater than those of second transition series. For the third transition series, which is due to lanthenoid contraction, cancel this increase and the value of atomic radii due to similarity in the size of the element of the two series. Particularly, the group resemble each one closely in their properties than do other elements of the first and second transition series. The example of the pairs of elements which show similar properties and hence are difficult to separate are ZR, HF, and NBTA, or MOW, RUOS, RHIR, PDPT, and AGAU. The atomic radii of the elements of the three transition series are given below to justify the statement. Now, lanthanoid compounds. Lanthanide forms oxides, hydroxides, oxosalts, halides, and hydride. Summary: the present unit covers all the important and the interesting aspects of lanthanide, such as their electronic structure, oxidation state, ionic radii, and lanthanoid contraction, consequence of lanthanoid contraction, and the extraction and the various methods employed for the isolation of the elements, and a brief account of lanthanide compounds. The readers can understand well as these aspects after going through the unit test. So this is all for lanthanides. Thanks for watching.